So today's notes, guys, are listed as 702 on your roadmap because 701 in the notes was the bounce with the beat assignment. So this is kind of picking up with some of the stuff that you hopefully were able to fill into that sheet yesterday, and obviously adding some more to it today. There is only one playlist, guys. If you haven't looked at the roadmap, there's not 3 playlists. There's only one. Okay, this unit is very short. So let's go ahead and get to it. There's only 2 sets of notes that we're going to go through together in addition to the bounce with the beat notes. So make sure that you're writing stuff down because otherwise you're going to have a hard time completing those assignments in playlist 1. So this is from the assignment from yesterday, that bounce with the beat. It asked you to draw some free body diagrams, and so I'm showing you here obviously a more slow motion version of what you guys were looking at yesterday. And if I asked you to draw the free body diagram for this position at the negative amplitude, and that was one of the terms in yesterday's sheet, then you should have drawn something like this. Of course, we're going to draw FG. FG is always going to be pointing downward. Okay, but what other force do we need to add to our diagram? The spring force. Okay, and if the mass is located at this lowest position, then my spring force at that position is going to be pulling it back upward. And so you'll notice that I drew my spring force. And I drew my spring force with a greater magnitude. It is longer than FG, and I have to do that because otherwise my spring wouldn't be turning around. Okay, because as it approaches that lowest point, that negative amplitude, it's going to slow down, it will momentarily stop, and then it will come back up, but it's going to be accelerating upward the whole time, and so my free body diagram should indicate that with a net force that is upward at that position. Again, if we drew a free body diagram for this same spring or mass oscillating at the equilibrium position, then again I still have FG, and it needs to be the same length that it was a second ago because the weight is not changing. The only thing that does change as this is oscillating is my spring force. And at that position, at equilibrium, my free body diagram is also showing equilibrium of those forces. That I have equal and opposite forces here. Spring force upward, equal in magnitude to FG downward at that position. You also drew a free body diagram whenever the spring or the mass spring system was at its highest point, that positive amplitude. And again, you have to draw FG. Okay, but at this position, you should have figured out that your net force does need to be downward. Okay, but not just that. When the spring is compressed like that, that spring can actually exert a spring force that is downward as well, which of course would give me a net force that is downward. It is a restoring force, and we're going to talk more about that term, but it's going to try to restore the spring back to its equilibrium position. So whatever direction that is, in this case, that would be downward to get it back to equilibrium. That's the direction that that vector should be drawn. Okay, we'll go more into it today, obviously, but I know some of those terms were kind of scattered throughout that assignment yesterday. Some of those definitions were in there, and some of it you had to fill in on your own. But this is, or these are some of those free body diagrams that you were asked to draw. So your paper asked you to draw minimum amplitude and maximum amplitude, and the wording might have been slightly confusing, but what I'm talking about here is my negative amplitude. And so my negative amplitude would look like this. We already drew this one a minute ago. But we can also take a look at what that would look like, my second law equation for this free body diagram at that position. We've been deriving second law equations all year, so let's go ahead and figure out what that equation would look like here in case we did need to do a derivation or in case we do need to do math to determine things about our mass at this position. So again, I know that the acceleration of my mass is equal to F net divided by that mass, and I know that my net force here is the result of these two forces, my spring force plus Fg. I do know that Fg is negative, okay, and so whenever I take a look at it, the equation for spring force is negative K times X, and when I look at Fg, it's really mass times negative g, since that's the downward. If I call the downward direction negative, which I have already done so by labeling it as negative a over here, but it ends up looking like this. And what is my displacement? In that spring force equation, that x represents your displacement from equilibrium. At this position, that displacement is negative a. So I could substitute that in as well and have negative k times negative a, where that is my negative amplitude, minus mg. Okay, of course, when I go and multiply this, I will have a positive number here, which I should because it's pointing up, and this will be negative, which it should be, it's pointing down. Okay, and then you can, of course, solve from here if you had some numbers to plug in, or maybe substitute something else in if you're trying to solve for something that we don't have on the screen right now. Okay, but that would be at least a starting point for that derivation at minimum amplitude. You could calculate the acceleration as negative spring constant times that negative amplitude minus the mass times that gravitational acceleration divided by mass. You were also asked about equilibrium position, and of course we already have the diagram here, so again we can derive that equation, but this one's a little bit easier because Fs and Fg are equal and opposite in magnitude at this position, giving me 0 acceleration because I also have 0 net force. And so I can come up with this equation here and just say that my spring force is equal to my Fg, or I could even say negative kx equals mg. You could, again, substitute those things in, depending on what it is that you were trying to solve for. But in this case, I do know that these are equal to each other and that my acceleration of the system is 0 at equilibrium. Again, this may or may not already be written on your Bounce at the Beat sheet, so you can add it there or you can just add it to your notebook. The other position you were asked to analyze was at maximum amplitude, and again, if I take a look at the equation now, my net force is my spring force plus Fg divided by m. Again, both of these forces are going to be negative, which you see as soon as we substitute in those equations. I have negative kx plus negative mg divided by m. And again, my amplitude here can be substituted in for the x. This time, though, I'm at my positive amplitude, so I just have negative k times positive a minus mg over m. So again, you can derive these equations and then solve accordingly. We don't have any actual problems right now, but just to show you how to derive those second law equations for our mass on a spring system at these different positions during its oscillation. Does anybody have any questions about those derivations? Yes?
In the case of the Bounce at the Beat, how is the spring force pointing down?
How is it pointing up?
Down.
Down? Because when the spring is at this position, and I'm going to go over this in just a second, but the spring force is a restoring force. It's always going to push or pull in the direction toward equilibrium. So it's going to be in our notes. So we can get to that in just a second, and you can all write that down in just a second. But yes, you're going to see that with the spring. It is always going to bring you back toward equilibrium if you have displaced that spring. All right, so we're going to talk today about simple harmonic motion. That is the title of the entire unit. And simple harmonic motion describes an object with repeating motion through the same positions and velocities over some definite amount of time caused by a restoring force. I just mentioned one type of restoring force, which we're going to look at a little bit more as we talk about springs and mass on spring systems. So again, simple harmonic motion describes an object that has repeating motion through the same positions and velocities over some definite amount of time caused by a restoring force. If you need to write these things down and I'm going too fast, please open up the notes on your own screen. That way you can get everything written down. Or try a little bit of a summarization or shorthand so you're not writing every word. I am on slide 12 if you are still trying to write, but I'm going to go ahead and go on. Restoring force refers to any type of force that tries to return an object back to equilibrium position. Springs will do this. If you compress a spring, it will push back against you toward equilibrium. If you stretch a spring, it will pull back against you toward equilibrium. And so that spring can provide a restoring force, a type of force that tries to return the object to equilibrium position. Equilibrium is going to describe the natural position or rest position where the net force is 0. So yesterday when you did the bounce with the bead activity, you hanged that spring on the ring stand, and before you added any mass to it, that spring was at its equilibrium position. And as soon as you added a mass, of course, you caused displacement of the spring, and then you got that oscillation because you had that restoring force trying to return the object back to equilibrium again. A term that you need to know, and again, this was in yesterday's assignment as well, but period is one of the variables that's going to show up in our equations. It is the time for one oscillation. The symbol or variable for period that you will see on your formula chart and that we will use in here is a capital T. It is a time, but it's not just any amount of time. It is specifically the time for one oscillation. And so we use a different variable than just a lowercase t to indicate that. However, it is still measured in seconds, so we do have the same unit we would for any other time. And the equation for the period of an oscillating spring, which you were asked to look up on your formula chart, so hopefully you found this already, is the period of a spring, that's T sub s, equals 2 pi times the square root of the mass divided by the spring constant. Okay, so that is the equation for calculating period if you have an oscillating spring in simple harmonic motion. You need to know the mass, and you need to know the spring constant of the spring. All right, so when we take a look at something oscillating, yesterday ours was oscillating up and down, but you can also take a look at spring oscillating back and forth on a horizontal surface like this one. And so here it shows the middle picture is showing equilibrium. And so this is where it would be when it was at rest. You can pull the spring this way to cause extension, and when the mass moves to the right of equilibrium, I'm going to call that my positive direction. Again, you do need to start by defining the direction, but as a general rule, in a convention, we typically say that right is positive and left is negative, just like you would on a coordinate system in math. You could label it otherwise, but I'm going to stick with that convention for these notes. So anything to the right of equilibrium, I'm going to call positive displacement. Anything to the left of equilibrium, I'm going to call negative displacement, and equilibrium I'm going to define as a position of 0. Okay, and so you're going to have this oscillation about 0, going in the negative and then positive directions and back again. Your amplitude is the maximum displacement away from equilibrium, and there is one on each side. As that spring completes those oscillations, it will reach maximum extension, and that's going to be your positive amplitude, and then maximum compression, and that's going to be your negative amplitude with the way that I've defined the directions here. Okay, but that amplitude is the maximum displacement. You'll see it labeled here as negative A and as A or positive A. You can also see it in this moving animation. So this is what it might look like if you had something oscillating back and forth on a frictionless surface. And in this example, I'm going to have negative displacement anytime I am to the left-hand side of my equilibrium position. I will also have negative velocities if I'm moving to the left. So you'll notice that as this thing moves this way, right now it has negative velocity, but then it stops and turns around. So when it moves to the right, you have positive velocity. Note that you can have a negative velocity even if your displacement is positive and vice versa. Okay, this region over here does represent positive displacement, and I will have positive velocities when it moves to the right, but in the other part, when it's coming back, those are going to represent, of course, negative velocities. So again, you can have a negative velocity in a positive region or vice versa. They're not the same thing, but you do have positive displacement over here. You do have negative displacement over here. All right, what is the velocity at the amplitudes? I heard it whispered a couple times. What's my velocity at this point right here? 0. Yeah, at the amplitudes, your velocity will be 0 because they represent the maximum compression or the maximum extension, and that means that at that point, this object has to stop moving one direction and turn around and go the other direction, which means it's momentarily 0. Okay, so at your amplitude, you have velocity of 0. Where would your system be moving the fastest then?
Middle.
In the middle. Yeah, directly in the middle. Because as it moves back, from the positive amplitude this way, it's going to speed up until it reaches equilibrium, and then it's going to start to slow down again. Okay, so at equilibrium, you will have the fastest speed of this object. And I say speed because it's obviously continuously going back and forth, so the direction's changing. But the speeds there at equilibrium will be where it's the fastest. All right, so again, this acceleration that we see occurring, these change in direction and the speeding up and slowing down as it moves throughout this oscillation, is the result from the net force at that instant. Again, simple harmonic motion will always involve a restoring force. So when we look at the net force, we know that there is a restoring force. Sometimes that's the only force acting on the object. Okay, in this particular case, it would be. But for a mass on the spring that's going in this direction, that restoring force and that net force will be your spring force. Now, when we had it hanging and going vertically, of course, we had to also take into account Fg. But in this situation where it's moving horizontally, my net force is my spring force. It would be the only force acting on this object as long as there's no friction on that surface. And so you can see here, I've added these vectors to my animation. You can see as the position's changing. You can also see the restoring force changing. And again, it's always pointing inward toward the equilibrium position. All right, so what would my net force be at equilibrium? We already looked at this when we drew the free body diagram from yesterday. You can kind of see it here as well. My restoring force when it reaches this middle line is momentarily 0. And so that's exactly what we would say. At equilibrium, my net force will be 0. At the amplitudes, on the other hand, and you can see it here, those vectors are the longest, representing the greatest magnitude of net force. And so we would have the maximum force at the amplitudes, okay, whatever that might be for that system. Okay, but you're going to have maximum force at the amplitudes. You're going to have 0 net force at equilibrium. And so what does this tell us about the acceleration of the object? Well, if I have maximum net force at my amplitude, that means I also have maximum acceleration at my amplitude. If I have 0 net force at equilibrium, it means I also have 0 acceleration at equilibrium. Okay, and so you need to keep these same things we've been talking about all year. The same principles are going to be applied to this situation. Even though it looks a little bit different, we have this constantly changing force, which we haven't really had to deal with, well, other than circles. All right, so again, at equilibrium, your net force is 0, thus there's no acceleration. Acceleration is maximum when there's a change in direction. That's going to happen at the amplitudes. So again, this is just summarizing the stuff that we just talked about. All right, so if we wanted to take a look at the relationship between the variables, I know net force is m times a. I know spring force is negative kx. And if I'm talking about my net force at my amplitudes, then I would have that maximum acceleration. So I could do this. I could say that my mass times my maximum acceleration is equal to negative k times that maximum extension or compression. And I could derive an equation and say that my acceleration is equal to negative kx over m. Okay, and this would be an equation you could use to determine that maximum acceleration of a mass on a spring as it's oscillating if you had these other variables. Okay, so negative kx divided by m. All right, so when we take a look at this, because you have a constantly changing force and therefore a constantly changing acceleration, we cannot analyze this in terms of kinematics, and that was one of the questions yesterday. You can only use those kinematic equations if you have a constant acceleration. And it's going to be really difficult to analyze it in terms of or to get that information because these things are constantly changing, that, you know, our F-net equations aren't going to be super helpful either unless we're comparing 2 points specifically, because it is constantly changing. So it's going to be easiest to analyze this in terms of energy. Okay, and so oftentimes we'll be looking at the energy of the system, energy of a mass on a spring, and we're going to assume that we have a frictionless surface, and that's an isolated system so that we have no external forces acting on it. The only force here is going to be that spring force. Okay, and so at my negative amplitude, we've already talked about the fact that it's temporarily at rest, momentarily at rest. So its KE, or its kinetic energy rather, at that point will be 0. Kinetic energy at the positive amplitude, also 0, because again, at those specific points, this object is changing direction, so it's momentarily instantaneous velocity of 0. Okay, at equilibrium, however, I have maximum kinetic energy, whatever it may be. Again, depends on that system. What about gravitational potential energy? Do I need to take that into account for this system? No. Okay, if I was doing a vertical spring, yeah, but not for this. And so those are 0 everywhere. Okay, we're just going to call the surface a height of 0. We don't have to worry about UG. But I do have to worry about elastic potential energy. Okay, I know that the equation for elastic potential energy, U sub S, is 1/2 kx squared. And so I know that the positions where I have a greater amount of displacement of my spring, that's my x, is where I'm going to have more spring or elastic potential energy. And I have the most displacement at my amplitudes. That's what they are by definition. And so that means that I'm going to have maximum spring force at my negative amplitude. I'm going to have maximum spring force at my positive amplitude. And again, you can even see it in this diagram. When this thing reaches equilibrium, that spring force, that restoring force, is at least temporarily 0. Okay, and so we can analyze this in terms of energy. That is one way we can approach these problems, is by looking at it in terms of energy. And of course, we could, you know, if we had some numbers to throw at it, we could start deriving equations and start trying to solve for some things. Okay, now if you have a system where there is external work done, if it's not an isolated system, for example, maybe that surface did have friction, then you would have something occurring called dampening. Okay, and dampening occurs when the simple harmonic system has an external net force doing work on the system. The most common forms of this are air resistance and friction. The work done to the system causes that system to lose mechanical energy, and this means that each oscillation is going to get smaller and smaller and smaller until eventually the system just finds itself at rest. If you had let those springs oscillate long enough yesterday, and some of you probably did, it probably did eventually come to rest because of these dampening causing the dissipation of energy from the system. Okay, we can't entirely get rid of it in the real world, but of course, when we answer AP Physics 1 questions, everything's always ideal. Okay, unless we tell you otherwise. All right, so energy is one way that we can analyze these systems and calculate things. The other way is a little bit more abstract, and that is by connecting this unit with the last one. By taking these objects that are moving in simple harmonic motion and taking a look at how they behave similarly to objects moving in uniform circular motion. For example, if you look at a uniform circular motion object from the side, it appears to be in simple harmonic motion. If I only look at the y velocity of this red circle that is moving in uniform circular motion, it has the exact same y motion, y direction, as my object over here oscillating on a spring. And I could graph their position time, at least in the y direction, would look identical. Okay, and so we can connect it to uniform circular motion in order to do some of our math as well. So it doesn't have to be energy. It can also be in terms of circles. So now we're going to talk about how we can relate simple harmonic motion to rotation. Please write this down, guys. This part is, there's a lot of things in physics that I would say can be kind of, maybe not common sense, but you know, you can easily see it. This one is a little bit abstract. Okay, so I drew a circle down here, and I drew this circle so that its diameter is equal to the full range of motion of my oscillating object up there. So I have going from negative A to positive A. Okay, and we're going to take a look at how would I determine the position of this block right here. I just picked a point. Pause the animation, pick a point. Okay, and so we're going to talk about how we would determine its position here, because again, we can't use kinematics. We have a changing amount of force and thus a changing amount of acceleration. But what I can do is relate it to circles. So I have drawn in the center of my circle and a radius going from that center to this point where I have intersected my circle right here. Okay, I know that I can also draw in a line of radius out here to the amplitude, and that I could relate these things to each other. But if I wanted to determine, okay, the change in linear position here, it's going to correspond to my change in angle here. Okay, so I'm going to be looking for this change in angle, and again, we're going to be relating this linear motion, this simple harmonic motion, to this circular motion. Okay, and this change in angle that occurs, I can calculate the angular velocity. Again, our angular velocity equation was our change in theta, delta theta, divided by time. Okay, that's the equation from last unit. Okay, so how do we find that position, this linear position, at this point? Okay, well, we're going to draw that line back in. Okay, and we're going to focus on this triangle that is formed. Okay, the position at that point is going to be represented down here. My position x at my time t1, whatever time. I just called it t1. Okay, and I have this thing labeled. I don't know what it is, but I do have my radius right here, and I can see that that forms part of my triangle. And so I can go to trig. Okay, if I wanted to determine, I can get a relationship between these three variables, r, theta, and x sub t1, my position at that time with this equation. Cosine of the angle theta equals, and again, cosine is the ca and SOHCAHTOA, adjacent over hypotenuse. This is my adjacent side, my x, and this is my hypotenuse. Okay, so I have cosine theta equals x sub t over r. If I rearrange it, it looks like this. Okay, and so I can determine that position at that particular point with this equation, r times cosine of theta. Okay, now what is this value for r? Okay, this value for r is the same as this length we drew here for a. So that radius is actually the amplitude. And so I can substitute that in, and I can have my position at any given time is equal to my amplitude times cosine of theta. Okay, and I can also plug in something else for theta here. Okay, if angular velocity is theta over time, then theta is angular velocity times time. And so I can substitute that in. Again, depends on what information you have, but if you have angular velocity and time, this would be more useful than this. Okay, and so now I have my position at any given time equals amplitude times cosine of my angular velocity times time. Okay, again, in simple harmonic motion, we have objects moving in a repetitive manner. If we want to solve things in terms of time, we can use frequency. We used frequency last unit. Okay, we talked about, instead of angular velocity, it was like it has, 100 revolutions per second, the helicopter blade or whatever. And if we wanted to convert between frequency, the number of rotations or revolutions per second, and angular velocity, I don't know if you remember this from last unit, but what we did was we multiplied by 2 pi. So we had 2 pi times our frequency times time. Okay, and now we have something that we can work with. Again, it depends on what information you're given. But now we have an equation to determine the position of an object in simple harmonic motion at any given time with respect to its frequency, its amplitude, and the amount of time it has been oscillating. Okay, so this is that equation to determine the position at any given point in time, because again, we don't have a constant acceleration. Otherwise, kinematics looks so much easier, doesn't it? Okay, but we can't use it. This equation is how we can solve for position with respect to time for all of simple harmonic motion. I'd write it down if I were you. Okay, it is a good starting point for graphical analysis, because guess what? We also have to graph this. Okay, so let's go ahead and do that. Let's see what a position time graph would look like for an object in simple harmonic motion. Okay, we know that our maximum and minimum positions, this is a position time graph, we know that our maximum and minimum are going to be positive A and negative A. So we can add that to our axis. We have positive A, 0, negative A. So what would my position be at a time of 0 seconds? In other words, if my time was 0, look at my equation, I would be taking the cosine of 0 in radians. You do have to be in radians. Anybody know what the cosine of 0 is? 1, which means amplitude times 1. Amplitude. Okay, that means that at time 0, I would be at the amplitude. Okay, and so we can plot that point. Here's my point. Time 0, I'm right here at amplitude. Okay, and so we have that starting point. And we know that this object is going to be, if it's starting here, it's going to be coming back towards equilibrium, and then it's going to go past it to negative amplitude, and then it's going to turn around and come back towards equilibrium, and then it's going to continue this pattern. Okay, and so this is what my graph is going to look like for my position time graph for this object in simple harmonic motion. All right, so I still have that graph up here. This is my position time graph. So now we're going to talk about a velocity time graph. How do I get velocity from this? Guys, where would my velocities be 0? How do I get velocity from a position time graph? Let's start there. Ignore this picture. It's slope, right? Okay, so it's asking basically where those slopes are 0. Okay, and of course, we already know that, we talked about it with the animation earlier, we already know that we're going to have those velocities of 0 at the amplitudes, because it has to turn around. But it's also a slope of 0 if you draw on the tangent line at those points. Okay, you would have a horizontal line at each of these points. The velocities in between these points, we also find the slope. Okay, so pick points. My slope here, it's a negative velocity, whatever it is. My slope here is a positive velocity, negative, positive, so on and so forth. And now we're going to take this and use this information to plot some points on our VT graph. So I know that at time of 0, my velocity is 0 because we said that velocity was 0 at the amplitude. So my starting point is going to be at the origin this time. Okay, and I know that from that point, I need to have a negative velocity. I need to start in the negative direction. And so my next point is going to be down here. I'm going to approach a maximum negative velocity. And then I'm going to go back to 0 again. And then I'm going to go to a positive maximum velocity, and then 0, so on and so forth. Plot the points. This is not going to be perfect, but we're going to connect it with a curve. Okay, you want it to look like something like this. So that is what my velocity time graph would be. Again, I started by just plotting points. They're green on my screen. And then I connected them as smoothly as I could with a curve. You should do the same thing on your paper. All right, so now we have a VT graph for our object in simple harmonic motion. Okay, is this still a cosine function? We know this one was a cosine function because our equation was position is equal to a times cosine 2 pi ft. Is this still a cosine function?
No, doesn't it start at a different...
Yeah, definitely not starting in the right spot to be a cosine function. What is that? Sine. But you might be thinking, but Ms. Darwin, sine functions normally go up first. So guess what? This is a negative sine function. Okay, and so I can write my equation like this. Okay, the velocity at any given time, because again, my velocity is constantly changing as well because I have a variable acceleration. My velocity at any given time would be equal to negative Vmax times sine 2 pi ft. Okay, so it's a negative sine function. All right, so again, that's why I told you this is a little bit more abstract than our kinematic equations, isn't it? But we can't use those. So we have to either use energy or this. All right, so what about max velocity? Okay, so how do we find that? Again, we know that velocity is radius times angular velocity if we want to relate it back. Okay, and we know that angular velocity is 2 pi f, and that radius is our amplitude. We've gone through this, relating it back to that circle again. Okay, and so if I wanted to determine that maximum velocity, it is a times 2 pi f. That would give me my maximum velocity if we wanted to solve for it. Again, we're just coming back to this equation from last unit. So these things do relate to each other because objects that are in uniform circular motion are also in simple harmonic motion. They have a repetitive motion as well. All right, so we have our xt graph, we have our vt graph. Now let's do our at graph. Okay, so one more graph. How do we determine the acceleration of an object in simple harmonic motion? Again, because my force is constantly changing, my acceleration will as well. Remember, acceleration is 0 when F net is 0. Okay, so here's my axis so that I can draw it. I have a positive A max, negative A max. We're going to plot maximum accelerations and 0 acceleration, kind of like we did before, and then connect those dots. Okay, so when is the net force 0? Okay, at equilibrium, at those maximum, velocities. Yeah, maximum velocities where you're going to have 0 net force. Okay, because at equilibrium it's moving the fastest. At equilibrium there's 0 net force. And so I'm looking for my maximum velocities here, which is going to be these points. Okay, so where I have negative Vmax or positive Vmax is where I'm going to be at equilibrium. And therefore it's where my net force is 0. And that means it's also where my acceleration is 0. So those points. Okay, when does maximum acceleration occur? Again, that's going to be where you have the steepest slope. Again, just like we used slope on our xt graph to get velocity, you can use slope on your vt graph to get acceleration. Okay, that's going to be at your amplitudes. Where you have maximum spring displacement and 0 velocity, but that's where you're going to have maximum acceleration. It's where you have the steepest slopes. They're going to be these points right here. Again, use this to figure out what direction. This is negative A, positive A, negative A, positive A, negative A. Use that here. I need to start at negative A because that's what this point is. Here's my negative A. There's the positive, negative, so on and so forth. Connect it with a curve. Looks like this. Okay, so that is your AT graph. What kind of function is this? Negative cosine. Okay, it's not starting at 0 like the last one, so it's not negative sine, negative cosine. Okay, so now we have a negative cosine function. Okay, so I know I'm going to have negative cosine of that same function we've been doing, but we need to fill in what the acceleration is at time 0. Okay, and that's negative A max, because at time 0, I start at this point. So I have negative A max times cosine of 2 pi times ft, and that's going to be the equation I would need to solve for the acceleration at any given point in time, because it is constantly changing. Remember, maximum acceleration is also equal to this. Okay, so we could even substitute one into the other. We found this equation earlier. But again, these graphs show all simple harmonic motion in an isolated system. So you can only graph it like this if there is no dampening. If you have some kind of external force, it's not going to look like that anymore. Okay, and please don't forget to use radians when you are doing these calculations. All of these calculations that we did today, you do need to have that calculator in radians when you're solving for this if you actually do it with some numbers. Which means you need to know how to switch back and forth between degrees and radians when it comes time to actually take the AP test, because we know already that we've used both this year. All right, guys, for the rest of the class period today, you can work on playlist 1, which is due by the 10th, or those FRQ corrections. If you haven't yet done so, please register for that practice AP exam that the district is giving on the 13th. You have to register by this Friday so that they can get everything prepared and have the right number of tests and the right amount of pizza and all of that. So if you haven't yet registered, please scan the QR code on one of the flyers around the room. If you have questions as you're working today, please let me know.